So Weifang Lee from China has a PhD in environmental science by the University of Nankai, China. She's a senior scholar at the Tianjin Academy of Eco-Environmental Sciences, and author of many papers on odor assessment, management, policy, and control technology. She coordinates the National Key Laboratory on Environment and Odor Pollution Control of China. And unfortunately, because of the Chinese movement restrictions, she couldn't come here. But she was very kind to send us a video. So if you could put that video of Weifang, and we asked her as well what is being done in China, or sorry, in Asia, because we asked for each of them on their continent, what it is being done in Asia related to odor management. And she is going to tell us now.
Good morning, everyone. First, I would like to thank the President and the organizing committee of the conference for his invitation. It's a great honor for me to speak at the meeting. My name is Weifang Li from Tianjin, China. I'm a senior engineer of Tianjin Academy of Eco-Environmental Sciences, working in the State Key Laboratory of Odor Pollution Control. My researches include odor pollution characterization, impact assessment, and control approaches. Here are the research projects I have undertaken in recent years. Today, my presentation is the odor pollution of urban municipal facilities in China. This is the contents of the presentation. The first part I want to introduce is the odor pollution status of municipal facilities in China. According to statistics, odor complaints account for about 20% of the total environmental complaints, rank second only to noise. The top 5 sources for odor complaints are livestock breeding, domestic waste treatment, rubber and plastic products industry, cooking fuel, and chemical industry. The complaint from municipal wastewater treatment is relatively low, accounting for only 0.4%. In 2020, the treatment capacity of domestic waste reached 254 million tons, and the sanitary landfill and incineration are the main method of domestic waste treatment. Landfill, waste incineration, and garbage transfer are the main complaint objects. Food waste are the main component of the domestic waste, which is the main source of odor. By the 2018, more than 4,000 sewage treatment plants have been built and operated in China, with a treatment capacity of 195 million cubic meters per day. But the problem is the sludge disposal capacity is insufficient, and the degree of sludge resource utilization needs to be improved. In order to minimize the impact of odor gases from municipal facilities, the state has promulgated a series of policies and standards. Local governments can formulate more stringent local standards. The second part is about the chemical composition of odorous gases. First, let's take a look at the odor intensity of each link during domestic waste treatment. From the color change, we can see odor intensity of landfill is the highest, followed by garbage transportation. The second is about the chemical composition of odorous gases. The first case is from a typical landfill in North China. In terms of chemical contribution, we can see nitrogen compounds contribute the most, and ammonia was the most abundant compound, followed by oxygen compound, and ethanol and acetic acid was the main component. And the chemical contribution of reduced sulfur compound is relatively low, As to the odor contribution based on OAV calculation, the trend is very different from that of the chemical contribution. Reduced sulfur compounds contribute the most, especially in winter. They contributed over 19% of the odorants, while in summer, nitrogen compounds contributed significantly because the increase in the trimethylamine and ammonia concentration. The second case is from a food waste disposal plant in North China. Odor samples were collected at 4 sites. Generally, the chemical concentration at the outlet is the highest, followed by conveyor opening. The concentration at the residue tank is the lowest. In addition, the number and concentration of detected odorants increased in summer and autumn. This is the odor contribution of key odorants. We can see hydrogen sulfide was the largest contributor to odor pollution. Trimethylamine ranked the second, especially in summer. The contribution of trimethylamine increased significantly. The third case is from a municipal solid waste plant in South China. The main disposal methods include landfilling, anaerobic fermentation, and ecomechanical biological treatment. Landfilling is the main treatment method. Only a small part of municipal solid waste is treated by anaerobic fermentation and EMBT. Figure A shows the cumulative emission concentration of volatile compounds. Among the sampling sites, the highest volatile compounds concentration occurred at LB site in the landfilling area, which represents HDPE membrane break, followed by LW site, which represents landfill gas extraction well. The lowest chemical concentration was during EMBT. Figure B shows the percentage of each volatile compounds. We can see sulfur compounds dominated in all 3 disposal methods. The highest abundance of sulfur compounds was detected in the EMBT. Secondly is the oxygen compounds. This is the distribution of sulfur compounds. 4 sulfur compounds were detected at LB and LW sites, but at the other sampling sites, only carbon disulfide were detected. This is the distribution of oxygen compounds. The highest concentration was also detected at LB and LW sites, and the lowest concentration in the EMBT. This is the odor intensity of sewage treatment. We can see the odor intensity at the coarse screen and fine screen is the highest, reaching grade 5, followed by great chamber unit and sludge digestion unit, reaching grade 4. These pie charts show the chemical composition of odors in the main process of sewage treatment. In the pre-treatment stage, sulfide, especially hydrogen sulfide, is the predominant substance. In the biological treatment, oxygen compounds are the main detected substance. The sludge treatment stage mainly includes oxygen compound, aromatic hydrocarbons, and ammonia. The key odorants are sulfur compounds, aldehydes, and volatile fatty acids. The third part is the impact assessment of odor nuisance from municipal facilities. The traditional management process for handling odor complaints is as follows. Firstly, the Environmental Supervision Department conducts on-site inspection to confirm the existence of odor pollution. The next step is sample collection and pollutants analysis to judge whether the pollutants exceed relevant standards. Finally, ordering enterprises involved to rectify if exceed the standards. We can see the whole process is time-consuming. Furthermore, this method often fails to grasp the actual odor emission state. Therefore, in recent years, many industries and manufacturers and industrial parks has applied odor online monitoring system. The online monitoring system can detect the odor problem in time and give early warning and can also start remote sampling. Atmospheric diffusion models are also often used in odor impact assessment. However, there is no odor evaluation factor in current China's environmental impact assessment guideline. In the actual evaluation, hydrogen sulfide is mainly used as an indicator to study the scope of odor influence. The problem is existing studies seldom consider the impact of population exposure. In recent years, we have done some researches on the odor impact of population exposure. Here are two examples. One is about the odor influence of landfill height on residents at different floors of nearby buildings. Another example is odor exposure response relationship for wastewater treatment plant. The last part is odor pollution control measures in China. The state advocates the whole process control strategy, including source suppression, process control, odor purification, online monitoring, operation management, and safe operation. My presentation is over. Thank you for your time. Good morning, everyone.